11 o'clock and we had a bunch of other people sign up, but I don't, well, that they can join as they have the time available and they can catch up with the recording. So we don't want to hold up. It's 11 o'clock, so we're going to get rolling. If you have questions, please feel free to put them in the chat. And this will be available for recording and posted on the Create website. And with that, I'm going to turn it over to Chris. And thank you, Matt, for presenting today.
Here we go. I'm going to share number 2. You should be seeing our presentation start. So thank you everyone for joining us today for our session. So first things first, Create Energy is based on our work through the National Science Foundation, and you can see our award number on the bottom of our screen here. I would say on today's presentation, we're going to hear more about math power circuits and exploring the inverse proportion through the Arduino and IoT. This is something that I'm actually very interested in learning more about. The Create Energy has a tremendous amount of available resources through the createenergy.org. I strongly recommend that you view our website and take a look particularly at upcoming events that will be on the near horizon. And I can also say that there will be, in addition to these webinars that you see posted here, there will be additional in-person summer institutes coming online. And I have a feeling my own institute will be probably within the next 2 weeks listed on our website for sign up and enrollment. So you can see our innovation webinars coming up. And here's some workshops that, like I mentioned here, be on the lookout that there's a few more coming online. I would highly recommend, if you get a chance, to take a look at the KidWin virtual workshops as well, particularly the battery and the power grid. Those are some newer content that KidWin is starting and has developed. And I think that'll be a pretty good source of resources we can embed into our classroom. So, for the brevity of time, let's get into our presentation. Our speaker today is Matt Matilla. And Matt is an applied technical mathematics faculty member at the University of Arkansas in Pulaski, the Pulaski Technical College. And more importantly, he's got over a decade worth of integrating energy systems, data analytics, and emerging technologies into the workforce STEM learning. What I did not know until I read his bio was that he's also the founder of Next Gen Learning Lab Academy, an EFA-approved provider supporting homeschool and hybrid learners through the hands-on STEM, AI, and energy-focused programs. So without any further ado, Matt, I'm going to let you share screen, and you take it from here.
All right. Thank you so much for the introduction, Chris. Thank you, everybody, for joining us today. Good morning, good afternoon, for wherever you are. And I'll be happy to present to you the lesson for today that I actually did in my class. And let's get ahead and get it started. All right, so why this lesson matters. So I have 4 bullet points. Algebraic concepts often feel abstract to students. I believe it is ideal for students to actually get a grasp of the theoretical applications in real world scenarios. And when you talk about math, more often than not, they will experience or encounter lessons in inverse proportionality. And oftentimes it's normally memorized, but not really understood. And this particular lesson addresses that need. The third bullet point, this lesson grounds in inverse proportion, which is observable and has measurable data, wherein we'll be able to see the data visualization that corresponds with the math through IoT using ThingSpeak. And of course, students will see mathematics being operating inside real systems. And part of the learning objectives, of course, the students will build circuits using potentiometer, a resistor, and an LED. They'll be able to measure and visualize voltage, current, and power using Arduino's analog input. They be able to observe voltage, current, and having them inversely proportional with power, and of course power being constant at least in this particular experiment. And of course the relationship with the uh, voltage and current. And what we need to build the circuits, of course, we're going to need an Arduino Uno R4 Wi-Fi. This is the Arduino Uno that has the Wi-Fi capability, which is kind of different with the regular Arduino Uno R3, which is normally available on STEM kits, on Arduinos and other resellers out there. Of course, you're going to need a breadboard, potentiometers, LEDs, resistors, and such. These are particular items can be found on Arduino STEM kits. And of course, if you are trying to adapt this lesson into your class, it's easy to follow through instructions via Tinkercad. So everybody will have access to the Tinkercad. And once you get through that particular link, you can zoom in, zoom out. And if those of you who are or may not be familiar with Tinkercad, this allows you to do designs and circuits, 3D designs as well. And if you kind of wondering how to connect the components, of course, there's notes. Once you click on that note, it tells you what are those connections are. Like for instance, here you'll see A0 to middle pin C14. I can find it. You can find it on their breadboard right here, and all components are actually notated, so you won't have a hard time trying to find where should I be connecting uh, the components. There you go. And the next thing that you will do to be able to get the data from your Arduino setup is following through the setup procedures. Everybody will have a chance to be able to see them, or you'll have the document that will allow you to set this up. Let me see if I can open that document for everybody to see. Okay. All right. So how do you set up the Arduino Uno R4 microprocessor? Of course, you gotta have your device ready. And if you happen to own a Chromebook, it will be advisable to go to uh, the Arduino cloud. And once you're in there, all you need to do is to create an account. You can create an account for free. And once you're there, all you need to do is create new. And of course, you're going to choose Sketch because the Sketch is the one where it will allow you to put in your codes. And there's a detailed instruction on it for everybody that you could follow through. It's pretty straightforward. All the screenshots and the steps are pretty much laid out completely, so you don't get lost. And again, that is if you're using a Chromebook. However, if you're using a Mac, a Windows system, or a Linux system, you can just download the Arduino IDE to your device to be able to do that. Of course, once you have the Arduino Uno ready, let me show you the IDE that is open. So this is the Arduino window, wherein it's connected to the Arduino Uno R4, which that's connected through a USB port, a USB-C port to be exact, if you're using the Uno R4. Let me show you what the setup looks like. Okay, so as you can see from here, this is your Uno R4, and this is the USB-C cable that is to be attached to your device. As a caveat, you cannot have this USB-C on a regular Uno R3, so this is only available for an R4 Wi-Fi model. Some kits doesn't have this. I mean, you have to purchase this separately. But if you're buying a whole kit of Arduino Uno R4, it should be included. But otherwise, if you just need the board, it's sold separately as well as this one. So these are, of course, your half a board, and these are the connections. This particular 3D printed device is something you can find online. It just makes you it's built to make it easier for you to do your tinkering or do your prototyping. So it's kind of slanted instead of flat on your table. Of course, in this particular slot like here, allows you to put the Arduino battery that comes with a kit if you buy one. And of course, when you go back to the Arduino window, you need to upload the code and make sure you verify it to um, have to make sure that your code's aligned with what's being compiled in the system. And of course, open your serial monitor at 9600 baud. And this particular chart right here gives you an idea if you are using the Arduino R3, the regular model. This is from the serial plotter themselves, and this is what you're supposed to see. The values 1 through 4 here can be configured with your code that you're with the code that you uploaded. And if you notice, the yellow lines and the green lines here are if you're seeing it real time, it's oscillating. And of course, these are either the current and the voltage being the opposites. Of course, they're being inversely proportional. And now here's the most important thing if you're doing the data visualizations with ThingSpeak using the Uno R4. Of course, it has a Wi-Fi capability. It allows you to connect your device to the IoT. And let me show you that. Okay. So once the link is available, of course, it'll be provided for you. All you need to do is sign up for a ThingSpeak account. So once you have a ThingSpeak account, it will ask you to create a channel. On my end, I already have existing channels here. So for this particular instance, you have to make a channel. Let's say I'm going to do a test channel. Field label, it's up to you, but let's say if you want to do that, you want to do voltage or current, what have you, save the channel. So at the moment, it's not reading anything. Of course, this is a sample walkthrough if you're trying to create a channel for the first time. And then take note of your API keys. So the API keys associated with your channel will tell you these are the things that you need to put in to your code that you will upload on the Arduino window or the IDE window, like this one here. So the SSID and password, it depends on your system, your network, if you're connecting to your home device or your home network. But otherwise, you can change it to your phone connection. If you're doing a hotspot, you can just change it. And once it's working again, um, you can upload the file or the code, verify, and then once it's connected, you will show these messages right here at the bottom. It tells you the reading is 1 volt. Of course, the intervals and this PWM is basically just a cycle, and all these data is connected to um, your ThingSpeak account. So let me go back to that and show you in real time what it looks like. So assuming that you already got your channels, let me go back to the one that I created previously. So this is all the channels. Basically, you only need to put in channels. Let's say you put in one, you created one channel and 3 different fields like I did here. You got a field 1, voltage across LED, field 2, current through the resistor, and PW, electric power, field 3. We'll get into this later on. So if you notice, these are all constant because I'm not actually turning the potentiometer. I'll go ahead and show you how the data will change. Let me see if I could. I'm going to show that particular. Okay, here's my second camera. All right. Okay, so I'm trying to share this link. I'm going to have to change to public view so everybody can see that. Okay, and see if I could type that into the chat. Okay, please try to click on the chat and see if you see the graph in real time, and then I'll show you what happens to the graph once I turn on the potentiometer knob. Okay. Can everybody see the website?
Okay, so I can see your website. I've got the ThingSpeak
Okay.
up, but no data change yet, but I know
Okay.
you're
Perfect.
working on it.
Okay. Perfect. That's what we want to see. All right. So everybody can see the setup right here, and it's on completely 0 right now, so you can't see the LED. It's turned off. So I will turn it towards clockwise slowly. This one. Hold on. Okay. Should be a little bit of change there. So as I um, turn it, I'm sorry, clockwise, gradually, you should be able to see changes in data. And then I'll go back to counterclockwise. You see that point going up from field chart 2. So again, a field chart 1 is voltage and field chart 2 is current. So you should be seeing opposite variations in the graph. And it's completely turned off now. Um, the settings for this is you can actually change. Okay, let me go back to the desktop window. Okay, so the settings for the field chart on this pencil icon, you can change the time scale. Time scale refers to a minute interval. Let's say if you put in 10-minute interval, it will only update the data that's shown on the graph every 10 minutes. And of course, we'll have 60 data points in variation. We go all the way to just 1440 minutes, and or when I will do it daily. It's up to you. And you could, if you want to see all the difference, you may have to change all three field chart settings right on this Apple icon. I mean, pencil icon, rather. And that's how you see the visualizations. And of course, if I may go back there, just to give you an idea, like you can gather up all these four graphs into one. You can embed it on a Google site. So now let's go back to the visualization here that's computed inverse proportionality constant over time. So you can do is MATLAB analysis. So once you do a MATLAB analysis, you create your custom code. You'll be provided with this one as well. So once you create that channel, all you need to do is take note of the original channel. Well, the three fields that are created are. You don't need the APIs for the MATLAB analysis. So the MATLAB analysis gives you the computed data coming from your original channel or your first channel that you did. So again, API keys coming from that first channel you created with the three fields. So save it and run. This is actually working, so you don't really need to get um, confused with it. It just tells you that there are too many frequent requests, but it's working, as you can see. And that's how you actually get an idea about creating those channels and seeing the visualization over time. So that's the computed data, and this is the cleaner version of the computed data, and this is the inverse proportionality constant over time that is taken into account. So let's go back to that. So here you can see the inverse proportionality between those two values. And of course, you will need an account. Like I said, take note of the API keys on the first channel that you created. Do a MATLAB analysis, and of course the visualization, which will actually have the smoothed plot values after you do the MATLAB analysis. But if you just want the visualization, that's fine as well. And why this works, it's a controlled constant power model. So we assume that power is constant all throughout. It clarifies inverse proportion. Students will be able to understand that mathematics describes system behavior, and models can be constructed with intention. Key takeaways to math becomes tangible, hands-on. Real data is tied to equations, of course. Um, Real applications of theoretical things that they actually learned in class. And there's a clear evidence of inverse proportion as we see in the constant cross disciplinary STEM thinking that is aligned with the particular activity. And if you're interested with doing this, you might want to allow somewhere between 80 and 90 minutes. But if you're holding a regular community college class, an hour and 15 minutes, be fine. And then The remaining minutes will be tied up to the next session that you have, probably doing student reflection and all that. Student reflection worksheet is going to be available for you guys, those who want to get that. Part of some of the student reflection prompts will be like, how does current change when voltage increases? Um, why does power remain roughly constant across the experiment? Things like that. And again, we want to emphasize that this is a controlled mathematical model, wherein in a normal DC circuit with a fixed resistance, voltage, and current are directly proportional. And that's Ohm's law. However, power is held approximately constant, allowing students to visualize graph and the relationship of current equals to 1 over voltage. And welcome questions if you have one.
So
Well,
I
go
have
for it,
one
Katie.
question, and I'm sure, Chris, you have more on the complex technical side. And this isn't necessarily that. But between the processes, do you think, like when working with students, do you think that they're more excited by building the circuits or analyzing the data, or when they can actually explain like the math concepts kind of behind what they're observing with the whole process? Because it is like there's a lot of different, things that they're doing with all of this. Like, what do you think the students really like the most with the whole process of what you're doing?
Okay. The excitement actually builds up. One thing I noticed was students, those who, when I thought here at community college, most students doesn't have hands-on experience with Arduinos or any kind of STEM kit. So if you're incorporating hands-on activities such as this, it actually ignites curiosity and engagement at the same time. In fact, before this, I started using the kits that I had from Create when I attended the program last summer. We did um, resistor analysis using the color codes and matching it with the I forgot that you gotta use the reader or something. So you gotta match the color codes on them, and that's where it started, and the curiosity just kind of builds on from there. And once they had the opportunity to build the circuit, that's when they kind of question, okay, so we have a LED go in here, but why does the LED doesn't really change that much in terms of brightness? And that's because the naked eye cannot really tell sometimes the difference, and it's logarithmic instead of something that you could actually pinpoint by the naked eye. Those are something that kind of interest the students. But when it comes to the clarity of the data, that's when they actually kind of get what's the math behind this because of the data that's connected to ThingSpeak. And of course, if you're using the R3, I did an R3 in the R4 in class. And so when you're using the R3, the students can only be able to see the graph through the serial plotter, but they cannot have the clear vision of what is really the proportionality between um, current and voltage, because it doesn't have that capability unless you're using IoT to ThingSpeak.
Thanks, Matt.
You're welcome.
I was going to follow up, and that was a great question, Gabby. And my question is, as you, the instructor, what are like this biggest stumbling block to get preset up, or you find with this exercise? One thing I find is with Arduino, some students get hung up on the Arduino. That I could see some connections. What, in your opinion, when you've done this, what are some of the big hiccups to be aware of?
Mhm. I think preparation is the key. So what I did was I have separate plastic bins wherein I put in all the components that was needed. So they don't have to have the whole Arduino kit that has all the all the components that you don't really know if you're not familiar with it or a first time user, you don't know what to pick. So being able to prepare all the components that are only needed for the activity and then putting it in a plastic bin for each group to hand out, be able to do, it kind of clears up, I mean, it smoothens out the process really. That's something that's to be conscious of when you're doing this.
Hey, anyone got any last minute questions for Matt before we call it an afternoon and get back to our winter snowy days?
I had a quick question just about the Tinkercad software, just because that kind of seemed, at least from the students that I've worked with and high school and that type of thing, that might be a really accessible tool. And so I just wanted to know more about how you could incorporate that or do incorporate just that part before the additional coding and other things like that.
Mhm. Yes, great question. Thank you. So, for high schoolers that are using or first-time users and even novice users of Tinkercad, I mean, I myself not really a big expert in Tinkercad. It actually helps you to build the components from scratch and be able to, I mean, as you learn as well to build the components yourself, it makes it a lot easier. If I'm gonna share the screen right here with when it comes to the interface. So when you're using Tinkercad to build your circuits, you have the basic components available right here. So you just drag and drop, and then what actually is the most vital component is when you if you're is putting in the notes. So these notes come from this right, the notes tool. So the connections here is, I'm sorry, laid out with the notes. So, hey, I have this component from A0 to middle pin. Well, this I have the LED had to connect it from the with the notes short anode to J20 or something like that, and this is the potentiometer, and this is all laid out. So if you have this particular link that's already made, the students can't mess this up. If they, let's say they make a change like that and all of a sudden, things happen like that, you can have those extra things. You can just go ahead and refresh the screen and it'll go back to the way it was. So they can't really mess it up and it still guides them what the steps are.
Cool, thanks.
You're welcome. And there's, I'm sorry, and there's also an educator account that you can um, sign up for Tinkercad. It's free. And there's a lot of different softwares available that can work on and learn from.
Wonderful. Well, Matt, this was an excellent presentation. I've got lots of notes.
Thank you. Appreciate the opportunity to present today.
Okay, well, this concludes our innovation lunchtime chat. Hopefully, everyone gets back into the swing of things and stays warm for the next week or two while we go through winter. And look forward to seeing anything else on our innovations coming up and the future conferences. Gabby, would you like to clear us for the end of the day?
Yeah, I just want to thank everybody for joining us, and we look forward to seeing you on a future Create webinar, and check out our upcoming workshops on the Create website. And have a great day, everybody.
Thank you, guys.
Thank you, Matt.
Thank you.
Appreciate it.
You're welcome. My pleasure.